Engineered items, and indeed architectural structures, are tested to see how they withstand vibration. This form of testing is called modal analysis. This short presentation is going to show you how Inventor will allow you to conduct modal analysis on this shock tower plate, which is at the heart of the front suspension assembly. Having opened up the shock tower front part, you may well find it already has a material assigned to it. Go into the drop down menu and select As Material to take away the blue chrome that's assigned to it. Only certain materials can be used for this analysis purpose, so at this stage we'll set the default material, and then later on in the process we'll look at the list of materials that we can use. Having assigned the default material then, we're going to go into the Environments tab and select Stress Analysis. There really only are two options available here: Stress Analysis Settings and Create Simulation. We're going to create a simulation. Up comes the Create New Simulation dialog box, and we're going to name this simulation Shock Tower Modal Analysis. Having named the simulation, make sure you check the Modal Analysis radio button just here. So essentially what Inventor's going to do is it's going to test this part to see how it withstands vibration at a range of frequencies. In fact, it's going to, by default, check the part at 8 different frequencies. Of course, we could edit that value, or in fact we could set a frequency range if we had a range in mind. I'm going to settle for the 8 settings by default, leave the rest of the settings and say OK. Now would be the time to assign an appropriate material. If we go to the Assign button in the Materials section, we're going to override the original material by clicking here under the Override Material heading. And when we click in this box, a drop down menu appears. If we click on the arrow, there's a range of materials that are available for this analysis. In this instance, I'm going to pick aluminium 6061. I'll say OK to that. The next thing that we have to consider is, how is this shock tower plate going to be constrained? How is it going to be held down while it's being tested? The best way to do that would be to try and mimic how the plate would be secured during its working life. I'm going to secure the plate through this hole and this hole. We'll do that by going into the Constraints area of the ribbon and picking Fixed, and up comes the Fixed Constraint dialog box. I'm going to select that hole and that hole. Of course, when you do it, you could select these other holes instead or as well. With those two selected, I'll say OK. Just as a point of interest, I'm going to go into the Mesh View option to see how the software breaks this plate down into polygons. We'll just manoeuvre that around to get a good look at it. And we'll see that as the software analyses this flat plate, the solid surface is broken into this arrangement of polygons. We can toggle between the model view and the mesh view. We're now ready to run the simulation, so under the Solve area of the ribbon, we'll click Simulate. And from the Simulate dialog box, just before I hit Run, I'm going to expand it, just to see if there are any warnings already in place, or if any come up while I hit Run. I'll say Run now, and the results are being computed. And there I have my results. In the results folder in the browser, there are 8 different sets of results for the 8 frequencies that Inventor has tested the plate at. Perhaps the best way to view the results is to click on the Animate button here, and I'm able to run an animation showing how the plate performs. If I click on it here, you can see the deflection in the plate. One important point to note is that the colour coding here for the relative deflections is meant for indication purposes. This isn't meant to be a true indicator of the amount of deflection. One thing to note is that you can perhaps get a better impression of what's going on if you use the Orbit tool while the animation's running. You can sometimes get a better impression of how the part deflects. I'll just stop that. So that's a useful introduction to modal analysis.